So
Okay.
I think we can start now.
Okay, so I'm sorry. Now we have Dien who will keep talking a bit for us like about short range structure of nuclei. The floor is yours, Dien. Thank you very much.
Thank you, Conrad. So hi everyone. I hope that you are healthy. I know situation getting bad. We're back to June, but we need to carry on, right? So yesterday we stopped at this slide. We are talking about using elastic scattering, and that can help us to extract the charge distribution and the charge form factor. So we are a little bit behind schedule, so I will directly continue from here without reminding some material yesterday, and I think it's kind of like warming up as well. So today, the first, I would like to go to one more example about what we can use elastic scattering electron to study the nuclear structure. And then we will quickly go to quasi-elastic, what we will use for the short range correlation. So that will be the main topic of our lecture. So we will get there today. So the next example is using elastic scattering to study what we call electromagnetic form factor of the nucleon. So that is different type of form factor, right? So in order to study that, we go a little bit slow in formalism. So what if I'm diagram I'm showing here is electron scattering off a proton at rest. So this one, it can be a nuclear target as well, but I'm showing here is a nucleon at rest. So that is why you see the momentum component is 0 here. So we have a four vector: incoming, outgoing electron, the target here, proton at rest, and the outgoing the proton for elastic, right? But this one is not always detected. It depends on what we want to measure. So from these four different vectors, we can build up the different invariant variable. So invariant variable here, it is a frame independent. So we can do it in any frame. So the one is the more important for it is the Q square and W square. So the thing is that now we want to extract it, the electromagnetic form factor. So we will go from the mode cross section. So the mode cross section here is a cross section of the electron on the nucleon with the infinite mass. And because the electron here, it carries the spin 1/2. So using this formula, we already take into the account of the spin of the electron. So I already showed the formula, the final formula here, but I highly recommend you to check out one document. It looked really old, like I think it from 1967. But I think when we go with the formalism, go from the thing from very beginning, it's a really good document. So you can show you, this document will show you how to build up the mode cross section from very classical picture and how they include the spin of the electron and many other factors as well. So I will send along with the lecture in the Slack about this document because I think it is so old. So I'm not sure you can even find it online yourself. So the thing is that I just mentioned that we assume that this mode cross section is on the target with infinite mass, right? But it's not true. So they have some mass and they will have the recoiling factor. So that is why in realistic, the picture, we need to correct it for what we call is a recoil factor. It defines. So I think that because of nucleon, it is not a point point light distribution. It have a electric, it have a magnetic distribution inside. So that is why in order to understand the nucleon structure, we need to include the form factor. So there are two form factors here, is F1 and F2. So this F1 and F2 will provide the information of the electromagnetic structure of nucleon. So this is one way we can write the form factor to present this cross section. We also can change it and write it in terms of GE and the GM here. So the what is the F1, F2 call is the Dirac and Pauli the form factor, and GEGM here is just form factor. So that carries the electric and magnetic form factor information of nucleon. And they can be the G and GM here. They can like present in terms of F1, F2. And there one variable here is the tau here. It determines equal to Q squared divided by 4m. So now you take a look at this form factor. You can see that they only depend on a Q square. So now if you measure, if you in experimental, you can control the Q square value at a fixed value. It means that you will measure the same GE and the GM. So that is what we want to measure in the experimental. So by some math, some changing the math
Can I ask
here.
you a quick question?
Yes.
On that slide, could you explain briefly why we use only 2 form factors? Do we only need 2, or would you perhaps eventually have to go to higher order?
So here we are using elastic scattering, right? Elastic scattering, EE Bryce measurement. So what you are measuring actually is just like angle and the momentum of the electron in the final state. Whatever is in measurement, you very much like have a 2 order of degree of freedom only, right? So the number of the form factor here, it also depends on the number of degree of freedom you have in the measurement. So it kind of corresponding to each other. So this one, it will be presented in terms of 2 form factors here. Yep. We go on.
I also have actually a really quick question.
Yes.
So I am familiar with on like deuteron targets that you need 3 form factors. So what is the extra degree of freedom?
Neutron form factor.
Or deuteron?
A deuteron form factor. Oh, so that one is due to another one. It maybe what you are talking here is related to kind of an atom spin level. Yeah.
I think it's something called like the quadrupole moment or a quadrupole form
Yeah,
factor.
so that one, the
Okay.
quadrupole one. Yeah, so that one is related to other one. Okay, so we need another degree of freedom. Yep.
Gotcha.
Okay. Yep. So now we can change the format in terms of the epsilon, the variable here. So yesterday there's someone asking me about Z epsilon, I think. So Z epsilon is the longitudinal, the component of the virtual photon. So if we can write in terms of Z epsilon right here, and we have a GE and GM, and I mentioned with you that the GE, GM at the fixed Q square, it is like fixed measurement, right? So now in experiment, we can measure this cross section, and we can calculate the mod cross section too with the recoil factor. So if we have a control at the fixed Q square, and then now we can like adjust the beam energy and the scattering angle to change this epsilon. So you can see that at the fixed Q square is constant, tau is also constant, right? You can calculate this one. And then now if you can change in theta E, scattering angle, and also the beam energy to have a different value of the epsilon, but at fixed Q square. So you will have a linear combination of the GE and GM square here as a function of epsilon. So so we have a reduced cross section here. Actually, it's the ratio of the cross section divided by the mod cross section, but with the recoil factor here. So this is the sigma R, reduced cross section. So we can write the term in terms of the function of the different value of the epsilon. Then we can use it linear fit in order to extract it to GM square and GE square based on this linear correlation. And this method is called Rosenberg separation method in order to extract it GE and GM form factor, okay? So this is one of the methods we are using unpolarized the cross section. So there are another method, it depends on the polarization measurement. So we're not going to this type measurement, but I just want to bring it up because it is the important factor for this one. So when we talk, yes.
Sorry, I just had a quick question, if that's all right.
Yes, sure. Yeah.
Yeah, sorry to interrupt. I was just when we say a fixed Q squared, you know, in an experiment, obviously, you know, not all measurements are going to be at the same exact Q². So what's kind of the tolerance band for considering something to be the same Q²? Is it like plus or minus a certain amount in GeV or MeV?
So when we talk about the fixed Q², so you're right, in the experiment, it may have some resolution, right? You never have a sharp one. So at least you have the distribution of Q², and that one, it depends on resolution and all the other factor experiment you are measuring, right? So as long as you make sure that, so when we talk about resolution, for the same measurement, you will have almost the same resolution. So even it have some spreading in the Q² distribution, but you need to make sure the central value of that Q² need to be the same. Then you can claim that we are at the fixed Q², like they have the same Q² measurement. Does that make sense? And how's the spreading of that measurement in experimental? It depends on how well you can control the resolution in your measurement. So it is not like, so you can think about it like very much like Gaussian, assume Gaussian with the width, right? But that width, it really depends on where you measure it and what type of detector you use to measure that one. So it can vary, but we don't say it as a fixed number, but the central value of that one, it has to be the same when you claim you have fixed Q².
Okay, so you just, so just to make sure I understand, so you just kind of choose like a fixed Q² and then you select points that are like within like a Gaussian width of that fixed value.
Yes, yes. You need to make sure the central value of that Gaussian one is the same when you claim you have the same Q² measurement. Okay.
Thank you.
Yeah. So another measurement here, it depends on like, it rely on how you measure the recoil the proton in the final state. And in that one, you will able to measure the two components, what they call the like polarization measurement here is a component of PX and PC, polarization of the final proton particle. And then for this measurement, you will not able to extract GE and GM separately. But what you can extract it is the ratio of the GE and GM. We're not going to discuss about this measurement, and I also not an expert of this measurement either. But the point to take away is that now we want to compare between the ratio GE and GM from two measurements. So the blue here is the from Rosenberg method we just discussed earlier. And second is the red one here is from this recoil polarization method. We expected them to be the same, but actually they have a very large difference between two methods. And it's still a big question for people to understand this question, why they are so different. And I think that they are one of the biggest assumptions, and people try to use it to explain this difference. It's called the two photon exchange. Because so far, whatever we are talking about, we are using the single photon exchange in the interaction, right? So when the picture change to the two photon exchange, it may be different. So our one photon exchange, it may not explain the picture very well. And for two photon exchange, I think it is very complicated one, and I will only can bring some reference paper for you, and you can check it out. So we will not cover the two photon exchange in this talk as well. Yes.
Yeah. So what's the difference between the hollow points and the solid points, the blue ones?
So they are the same at the same Q², and they just follow different measurement. So here it like it. So they calculate the ratio of GE² to GM² at the fixed value of Q², but follow different method. Okay. So the first method we are using is it like Rosenberg separation. So that is method 1. And method 2 is using the recoil polarization method. That one gives usage ratio as well. And then what they compare is the ratio of this one using two different methods. And
yeah, but we have two methods, right? We have two methods and three types of points. So what?
You're asking about this one.
Yeah.
I see. Let me see. Let me see in this one, what is it changing here? If I remember correctly, so this one and this one has the same Q square, but maybe they have the Q square different here. I will get back to you about the two, the blue different color right here. Okay. Yeah.
Yeah. Thank you.
Yep. Okay.
Hey, Dien.
Yes.
And what's mu p? Is that related to the polarization?
The mu p here is equal like magnetic moment here. So that is the corresponding to proton. It is for like it corresponding with the magnetic term of the magnetic inside the proton, the distribution. It's not a constant for the proton here.
Okay.
Yeah. Okay. Yeah. So this one with these two examples, we are having that like elastic scattering is very good in order to study about charge distribution for nucleon and nuclear. And it also the two in order to study about electromagnetic form factor of nucleon. So that is two examples we discussed in the elastic scattering. So now we will move on to quasi-elastic scattering. So like I mentioned before, so when we talk about quasi-elastic scattering, it is like, you can think about it like a picture of the photon, virtual photon, interact with a single nucleon inside nuclei. And this one will help us to study the cell structure and occupancy. And we will use it one to study the short range correlation as well. So before we talk about short range correlation, we said that we use quasi-elastic scattering to study the nuclear structure. So what we know about nuclear, what is nuclear and how we should understand it. So nuclear is the combination of the different nucleon. It can be neutron and proton, right? So the behavior of the nuclear, it depends on how the proton and neutron, they interact together inside nuclear. And that one can be determined by what we call is the nucleon like potential. So by this is one of example of the nucleon potential. So based on the potential, you can see that at moderated distance, the interaction between two nucleons is the attractive force. But then when they come to closer, like shorter distance, this interaction become repulsive. So we can practice it in like very much like how we can think about this system, right? What if it continue to be, it cannot be continue attractive at a short distance because of why? If it, when they come really close together and it keep being the attractive. So this one, the whole system will collapse into itself. Then we cannot have a nuclei. So we expected that at some distance, the force between the interaction should change from attractive to repulsive to make sure that we have a system existing. Yep. So now, what is the property we want to learn about the nuclear structure? And we just said, it is the bound system. So they combine the proton and neutron together. So it means that they will have an energy distribution. So that is what we will call it the NE, the energy distribution here. Other thing is that neutrons, they are not addressed. Like nucleon, they are not addressed inside nuclear. Then they will have a momentum distribution. And then we have another quantity, we call it the spectral function. So that is combination information of the both the energy and the momentum. So when we talk about the spectral function, it is probability of finding nucleon inside nuclear with a given momentum E and the momentum K and energy E. So one of approach to study this nuclear structure is that we writing the Hamiltonian. So this is the many bodies object. So we can write the Hamiltonian for this many bodies object. So that this Hamiltonian, it will be like kinetic term T here. Then it will include the potential between any two of the nucleon. And then another term, it like 3 treat any of the nucleon term and so on. So the thing is that if we can solve this many-body Hamiltonian, then we will find the wave function. After you have the wave function, you can calculate any quantity you want in the nuclear structure. But the problem is never simple, because in order to write it Hamiltonian, we need to understand how nucleon and nucleons interact together. And that interaction is a very complex one. It's not a simple one. So that is why the approach about solving this real, like many body Schrodinger equation, is nearly impossible with like many body system. So what we want to do in that way is that we need to make some assumption and simplify this nucleon interaction. So this both said like, oh, we make it simpler. And then we say that, oh, that is affected interaction into reasonable approximation. So after we have an affected interaction, we can block that interaction in the Hamiltonian. So now it will become affected model. So this is solvable problem. And then we can, based on different assumptions, we can study different aspects of this many body system as a nuclei. So when we have an affected model, like I mentioned in different affected model, we will have a different assumption. Then you may see different picture of the nuclear structure based on that. So in this talk, we will touch base with like two models, like Fermi gas model is one of simplest one. And the second one is shell model, independent particle shell model. That is one of the most successful one. So I highly recommend, I don't know if you use this book, but I think this book have a very good overview about the different like nuclear model. Like it also talk about Fermi gas model, shell model, and it explained in really detail. So if you want to learn more about step by step and in detail study of this model, I highly recommend this book to all of you to check it out. So now we go to the Fermi gas model. So the Fermi gas model is assuming that the nucleus is the combination of two independent systems, the proton and the neutron. So this is a very simple model. So in this model, what we assume is that now in this model, they can calculate electron coming in like through quasi-elastic scattering with a nucleon inside nuclei. That nucleon have an initial momentum pi and it knocked out with the final momentum is the pf here, and the transfer momentum is the q here. So we can calculate the initial nucleon momentum, like kinetic energy, based on like square root of pi divided by 2 mass of the proton, if that one is the proton here. Then we also can calculate the final energy based on this formula, and we calculate the transfer energy here in this model. So within this model, what they expected when electron to quasi-elastic on the nucleon, it should have a peak central at the value of the transfer energy plot with some sigma here. And the width of that, the peak will depend on the Fermi motion, and the width of that can be calculated depend on this formula. And the total peak cross section, because it's a two independent of the proton and the neutron system. So then it will just equal to combination of the Z is the number of the proton multiple to cross section of electron on the proton, and number of neutron on the cross section of electron on the neutron. So this is the expectation from this simple model. And then we want to take a look at the data and see if we see this behavior in the data measurement, and it's E. So this one is the data, I think, from what is the cycle in the very early the 1970s. So for this one, they do the measurement on the many different nuclei in this list right here. And we're only showing the picture of the few of them as example. This one is the cross section as the function of the transfer energy. So you can see that we see the signal, this pump right here, the peak right here, that is representing the quasi-elastic cross-section. And they are doing the fit like 2-parameter fit. So that 2-parameter fit depend on 2 variables, is the Fermi motion of the nucleon inside different nuclei, and this sigma right here, it is offset. So then this fit, like based on the expectation of the Fermi gas model, it really presents the data very well for the different nuclei. So you can see that from this measurement, we able to extract the Fermi motion of the nucleon inside nuclei for different nuclei. But you also notice that it worked well, like we see the behavior of quasi-elastic peak, but it looked like it should work well at the low value of the transfer energy. But at the high energy transfer, the data is way bigger than what we expected. So there are something else happening here, and we're going to take a look at that. So in the experimental, what we want to isolate is the quasi-elastic event. So that is what we do, like calculation prediction in the theory. But in experimental, we don't have that real isolation. You said, oh, I only want quasi-elastic event, but it never happened in that way. When you do the measurement in the data, you will have a different type of background, different type of event that come in too. You cannot just only only do the quasi-elastic in the experiment. So this is a very nice overview paper. It's talking about inclusive measurement EE price, and they have a toy model. This one is a very like toy model to calculate the cross section as a function of the transfer energy. They say the energy a lot here, but actually it's the same like transfer energy. So what you are seeing here is that what we want is a quasi-elastic event only. But in the high energy transfer, indeed, we have other process coming in too, like delta, like different resonance, and we also have a DIF. So what we really measure in the experimental is the total cross-section. So it is a mixing between quasi-elastic, different type of resonance, and the DIF event. So that is why at the high energy transfer, what you're seeing from the data is not purely quasi-elastic anymore. So we pretty good at identify the quasi-elastic peak, but we have this mixing problem. So in order to understand the quasi-elastic peak, we want to see a little bit more detail about that. How this quasi-elastic peak depend on different nuclei, how it depends on nuclear mass, how it depends on Q square. I think yesterday some of you asked me about like how to determine the quasi-elastic peak here. So first we take a look at how the quasi-elastic peak behave with the kind of like different nuclei. So here we have a fixed Q square value, and this is linear plot, and this is the same thing, but in the log slot. So we have a different type of nuclei here. So the red one is a deuteron. Magenta here is for helium-4, and the blue is for carbon-12. So you can see that for deuteron, you can see the quasi-elastic peak very clearly, right? But then when you go to the high, like heavier nuclei, this quasi-elastic peak kind of spreading out, it's getting bigger, and you cannot see it very well anymore. So this is how you can see it in the log scale here. So the reason for it is that heavier nuclei, you will have a higher nucleon momentum, like the nucleon in there, it have a higher the Fermi momentum. And because of it, the width of this quasi-elastic, it is broadened due to the Fermi momentum of nucleon inside nuclei. So when you have a higher nucleon momentum inside nucleus, it will broaden the peak more and more. So that is why you see it like more like wash out. You cannot see it very well anymore. So that is how the quasi-elastic peak, it depends on nuclear mass A, okay? So the next one, we want to study how the quasi-elastic peak, it depends on the Q square. So now we are using the same nuclei, but now we will changing. This is the measurement on the helium-3, and we changing the Q square. So you can see that here at the very low Q square, you can see the quasi-elastic peak is really big, very big, and the contribution of the other process is low. So you can see the ratio from here to here, right? So we can identify the quasi-elastic peak very well. But now when you changing, increasing the Q square value, you see that you still can see quasi-elastic peak here, but the contribution from the other term, like DIS and other stuff, start getting bigger and bigger. And when you go to high Q square, it looks like the other process is the dominant Z quasi-elastic peak. The contribution is getting smaller. So we can see that with the Q square much bigger than 1. So the contribution is dominant by inelastic scattering. Yeah. But now if you take a look at the low, even at very high Q square, but at the low value of the transfer energy here, this quasi-elastic peak is still like dominant. Like we still mainly see quasi-elastic peak, the quasi-elastic event at the low transfer energy. So this is some kind of perspective we want to learn about quasi-elastic peak to make sure that we're able to select the quasi-elastic event in the experimental, because it's due to the challenge, the problem of the mixing event. So we can handling.
Excuse me.
Yes.
Sorry to interrupt. Could you go back to the previous slide? Yeah. So
this one?
No, the next one.
Oh, okay, sure.
Yeah. Why do we not see the elastic peak here, or is it there?
Elastic peak here?
Yeah.
So it kind of like, let me see. So this is the from data. I think it's from helium-3. I think for helium-3, with elastic peak, it will be corresponding with the X around 3. So it needs to be in the lower side here. So I get the data here. It couldn't select the elastic peak on this measurement. It may be a lower here on this side. Yeah.
Oh, okay. Thank you.
Yeah. Yeah.
I have a question.
Yes.
So in my limited experience in SRC studies, we'll set a minimum Q squared of 1.5 or something, but no maximum Q squared. So that seems like the opposite of what we would want to do looking at these plots. So what's the advantage of setting a minimum Q squared for SRCs?
Q square is one variable. We also need to have X as well. Let me show you this. Yeah. We come back to it later, but I can quickly show you. So because the X, Q square and other variable, they have some correlation with other, right? So we want to have a high Q square, but we also need to go to the X bigger than 1 too, for the SRC. And you can see that Q square is 1 condition, and for X bigger than 1, it means that we stay in this area of the quasi-elastic to avoid all this, the messy background. So it needs to both Q square and X go together. It's not just only the Q square condition. Yeah. Does that make sense, Erin?
Yep, thanks.
Okay, yep. Okay, so we come up with a new concept. It's called scaling. So in a simple way, what scaling means? So the cross section, it will depend on the different kinetic variable, right? So in certain kinetic region, we can write the cross section in depend on a single variable. So for example, in the beginning, it depends on 2 variables, 3 variables, something. But in a specific kinetic region, we can write that cross section in terms of 1 single variable. And that single variable we call scaling variable. And the function, it describes that cross section depend on that single variable. We call it a scaling function. So if we see the scaling happening it means that it validates the scaling assumption. For example, we say, oh, in that region, we have assumption 1, 2, 3. And if you able to find that scaling variable and you plot the scaling function and you see it like very much like constant is the scaling or scaling. So you will say that, oh, so that assumption is working in that specific kinetic region. And if the scaling, the scale is breaking, it will indicate a new physics or our assumption is screwed up. We need another thing. So that is the idea about the scaling. So that will you to handle the quasi thing, and it also can handle in the DIS later. So for the quasi-elastic scattering, the scaling variable we call it Wise scaling. So I moderated the Q square and bigger than 1, we expected that scattering happen is quasi-elastic, and we will see this Wise scaling behavior. So what is the Y here? So Y here is the minimum momentum of the struck nucleon, and it in kind of parallel direction with the Q vector. So that is in terms of the quasi-elastic. So later on, when we go to DIS, we will see the different type scaling variable. It calls X scaling variable. And then we will talk about it more when we go to DIS event. For now, we will use the Y scaling to kind of like selecting the quasi-elastic event, and we see if it works. So the idea here is that, so I'm showing you here is the helium-3, the measurement with the different Q square. So from this plot, you can expect it that, oh, where is the low scale? On the left, right? Because on the left here, you can see the quasi-elastic here, peak here is more pronounced. So the contribution of it to the other part is bigger. So you know that also this one is the lower Q square. So quasi-elastic is dominant compared to other process. So now when you continue increasing this one, so go to the right, so you can see that first the cross section is drop. So it means that the Q square getting bigger. And you also see that the peak kind of more wash out and the other contributions start taking the dominant one, right? So this is the cross section with the measure from the experimental side. So in this Y scaling, I already mentioned that it is the minimum, the momentum, and it kind of like in the parallel to the momentum transfer, and it can calculate it based on the formula here. So now, what is Fy? So the Fy here is the scaling function here. So this scaling function, you can calculate from what you measure the cross section experimentally, and then you divide by the total total cross section of the Z multiple to element the cross section on the electron on the proton and the neutron on number of neutron to the neutron cross section here, and the sum kinetic factor. It is not important here. It's just like depending on the kinetic. So from the cross section, you can extract this Fy function, and it is plotting here. So you can see that, oh, you see all this messy thing is collapsing to one thing really nice here. So like everything like below like 0. So you can see that even this messy thing now, when you convert it to the Fy function, it behaves so similar together. So that is why you said that, oh, so now I'm seeing some scaling behavior. So everything can collapsing into one universal behavior right here. So you can see that, oh, so if I use the Fy function here, and then in the region where electron, so quasi-elastic, like electron, it takes place from the quasi-free proton or neutron in nuclei, we will see this behavior. So that is how we can use the Y scaling in order to isolate the quasi-elastic event. And then the thing is that what we want to study from the nucleus is the momentum distribution. So if we can, after you get this Fy scaling function, it is derivative of this function, then you will be able to extract it nucleon momentum distribution inside nuclei. So that is what we want to study. And this is follow E bright quasi-elastic channel. And now we take a look a little bit. This is some assumption. It get into this Y scaling. And I mentioned with you that like this assumption only can work in some specific region, and then it can break as well. And when it breaks, it means that that region, the assumption doesn't work anymore. So this one, I mean like some of the assumptions are like no final state interaction. It means that the nucleon is knocked out and it don't have rescattering with the remaining. And then like no internal excitation. So it means that it's A equal to 1 system stay in the ground state. And then like we can select up the smaller like negative Y. So no contribution of inelastic. And also don't take into account the medium modification, the EMC effect. We will talk about that later. So how well this Y scaling work? So I already showed you the case of the helium-3 right here. So it looked pretty well in the region where this assumption will work well in this area, right? You see scaling pretty nice. Now we go to the heavier nuclei. It worked reasonably well, but not that well. And that is why we need to consider about the other effect. The scaling, Y scaling work, but it also has its limitation because it not include many different effects, especially one of the big one is the final state interaction. So this one is shows the cross section here as a function of like transfer energy. So this is the delta, and they present the different calculation with and without the final state interaction. So there still have quite a lot.
Not for you guys.
Yes.
Okay.
Can I ask a question?
Yes.
So what's the significance of Y equals 0? And why is that the point where Y scaling stops working?
Y equal to 0, this one. So that is the peak of the, it is corresponding with the peak of quasi-elastic peak right here. Yeah, here. So you can think this is the Y larger, this is Y smaller than 0, and this exactly is the limitation of Y equal to 0 you're asking about. So after that one, it start picking up all the other background. So that is why where is that deviation. So that is how you see that. Okay. Yeah. Okay. Okay. So one of the things we consider here is about the final state interaction. Like all of this correction, it contributes to this Y scaling assumption, and it can make picture very complicated. So it's working reasonably well, but if we want to use this Fy scaling function in order to extract it, the true behavior of the momentum distribution, we still need to take into account all other correction in order to study that. So that is about like Fermi gas model, one of example. So now we're going to other model, affected model we call independent. Yes, yeah.
Sorry, I just had a quick question. This is just kind of going back to where you had those graphs of f of y plotted against y.
This one?
Sorry if this is a naive question, but what would be the physical significance of like a negative y? Because the y was related to the momentum of the nucleon parallel to the momentum transfer, but would a negative y mean like essentially you like hit the nucleon and the nucleon bounced back towards the direction of the incoming particle? I don't really understand the physical significance of, or what that would mean physically.
Oh, you mean like what is the minus y mean? How about it? So this is one in terms of language, I think it's kind of difficult, but if I can draw some diagram to see you how it works, it will be better. So maybe I can draw that diagram and explain to you in the Slack later. I think that way will be more productive. Is that okay? Like I can draw it, like explain in the draw. I think it will be easier to understand the concept. Okay.
Okay, thank you.
Yeah. Okay. Yeah.
Would you feel comfortable trying to annotate using the Zoom annotation feature?
Oh, I don't think I have it right here. So I don't know how to draw it in Zoom. So, okay, sorry about that. Yeah. Okay, so now but I will try to kind of like draw it in the hand and try to explain it and post it on the Slack to you. Okay, yep. Okay, so now we go to the second model about independent particle shell model. So what is this model assumption and what's good about it and what is limitation about that? So the assumption of the independent shell model here is that nucleon will move in a mean field it created by surrounding nucleon. So it means that you can think about the picture like one nucleon, it will the moving in the field that is created by anything else surrounding it. So that's the assumption about shell model. And the second important assumption is that no interaction at the short distance. So when you go to short distance, no interaction, it's just free. And the important feature about the independent particle shell model is that nucleon will fill up the separated energy level. And this energy level can be defined by the quantum number. And you will fill up by level, and the highest level, we will call it the Fermi energy level. And at this highest energy level, Fermi energy level, we will able to calculate corresponding what we call Fermi momentum. So this one is what we use a lot later. So you can think about the picture like this. So they will have a occupied the shell and they will have empty shell. In terms of energy and the momentum, the higher level will be the energy, Fermi energy level. And in terms of the momentum, it will only occupy up to the Fermi momentum as well. Nothing after that. That is based on the like model, independent shell model assumption. And in this independent shell model, they will ignore all the interaction between 2 and 3, 1. So this is completely out in the Hamiltonian. So they will only have one term. Here is the mean field 1. Yes?
Dien, I wanted to just like comment on that. Like, is this also agrees with, the QCD findings, like, the running coupling, we get like the color confinement, like in the low Q, and asymptotic freedom on the high Q. So is it also agrees with that?
Can you say it again? I didn't get your concern yet. Yeah.
So if we look at the running coupling in the QCD, then we see that, like, the coupling is very high in the low Q, and the coupling, like, which we call the color confinement. And also, like, if we go to the higher Q, the alpha, the running coupling is very low. So that means that it is that's what we call the asymptotic freedom. So I was wondering, like, if these models that we're talking about, like, are they do they agree with what we find from the QCD theory?
I don't think they can agree at that level, and you will see very soon what they can do and what they cannot do. Okay, yeah. So this is just very simple.
Can I add something just to answer the question? You have to remember that this model are no relativistic model for very low energy in nuclei. So you are really taking a small slice of the Q square that is when the nucleons are still nucleons, and you don't see quarks in this case.
Right.
So you don't have any concern about the running coupling.
I see. I got it now.
Yeah.
Thank you.
Thank you, Alex. Yeah. So this one we will have the mean field here is the potential they will use in this independent particle shell model. And the thing that you may ask the question is that this is very much in the nucleon level, like that Alex just said. So you can see that nuclear is a very dense system. It's a very strong interaction. So how come this independent shell model would work? Because we assume that it's very like no interaction at short distance or something, right? So the thing it helps this shell model working is based on the Pauli principle. Because with this principle, it will forbid the nucleons scattering to the occupied shell. So if that shell already occupied, the other nucleon cannot fuse that one. So because of this principle, it suppress the nucleon interaction by a lot. And this model is really successful in terms of explaining the ground state energy, excitation spectrum, spin, and particle. Like all of this one, it described in the very detail in the book I recommend you earlier by the Martin. So if you want to understand like how each of this one can be explained by independent shell model, I think that will be a very good reference. I just want to link this independent shell model to another thing we want to discuss is about short-range correlation. So that is one aspect I want to focus on here. So from this independent shell model particle picture, what we expected when we look at the momentum distribution. So we mentioned that it will occupy up to the Fermi level shell, right? So if that one is maximum, the momentum, it will corresponding to Fermi momentum. So based on that, we will expect that we only have a momentum distribution up to the Fermi momentum and nothing up here based on this assumption of the model. So now in order to test this model, what we will use is the quasi-elastic scattering E by P. So this is a diagram to remind you of what we detect and how we calculated the variable. So there are two new variables. You didn't see it up to now. Is the missing energy and the missing the momentum here. So what we are using, another assumption we put in here is the plane wave impulsive approximation. So just a few words about this. It is not a fancy name for assumption that only one nucleon interact with this virtual photon, and this nucleon does not interact further, like it coming out and it will not re-interact with this A-1 system, and we will detect this like knock out the proton. So that is what a plane wave approximation is. So within this approximation, the cross-section can be factorized to kinetic term and elementary the cross-section of electron on the proton, and what we other term is the spectral function. I already introduced this concept earlier. So with this type of measurement, what we try to do is that we will try to knock out this nucleon inside nuclei, and then we detect this one out, so that we can calculate the energy level of this nucleon depend on the different shell it stays inside nuclei. So that's why the knockout of the different shell, right? So we can see the distribution. So that one we will see from the data is that we can see the spectral function, this one in arbitrary unit, a function of the image here. So you can understand the image here is related to energy. It can connect to the energy of the nucleon at the specific cell. So you can calculate for a given cell what the energy should be there. So you can see the cell structure from this data. So you can see that, oh, for example, Z1 is energy level for Z corresponding shell, and then you can see that this is evident about shell structure. So now what we want to do next is that based on this like missing energy, the spectrum, we will able to isolate the different shell. So we select that one, and then what we're plotting is the p-mid distribution. So in this approximation, we can take it the p-mid as initial momentum of that nucleon, so that we can study about initial momentum of the proton inside nuclei. And the thing is that the data point here and the curve. So then what we compare is between the curve is the prediction from the particle shell model, and this is the data. So what you can see that the prediction from shell model describes the shape really well, and it agrees very well with data. But in terms of normalization, it's not. So when we think about the normalization, we will plot it here. So you can, if they agree with each other in terms of normalization, then the ratio is should equal to 1. But now, if you take the ratio of the data to the prediction from the mean field, you will see this ratio is about 0.6 here. And actually, it is like consistent behavior along the large range of target mass nuclei. So you can see that all of them is at about like 0.6 something. So the question is that the nuclear when they're missing, where did they go? Like we didn't see enough number of nucleon in like occupancy in the cell compared to the prediction. So some assumption in the mean field, it didn't describe the picture. So we know, and another thing we observe is that it not, yes, Erin?
Thanks. So is this averaging over all nucleon momenta, or is this assuming high momentum?
Oh, that is not for the shell, the calculated city for the valence shell. The two shell is kind of outer shell, two outer shell in the each of these nuclei. Yeah.
Okay.
Okay. So here, oh, okay. So here, another thing we observe is that in the area we assume to be empty shell in the mean field, because like we said that nothing above the Fermi momentum value, right? But actually we detect event, like we detect some proton like nucleon at the higher momentum compared to the Fermi momentum, and that is like where we're supposed to have an empty orbit. We see something here. So it looks like there are something to bring the nucleon from the mean field picture to above that. So what is approach we want to do is that, so for mean field, right, we completely ignore the two body, three body interaction, and we just assume it like a single particle in the mean field. So now it is the natural approach to start including another term to this Hamiltonian. So the next term we will take into is the two body interaction between nucleon and nucleon. So you may add that, oh, there are the long range interaction and also the short range interaction. So people already take into account of the long range, but that one, it didn't like account for the difference between the shell model and what we measure from data. So the next one we want to account to is a short range collation, and that can be one possible solution in order to account for the difference between the shell model and what we measure from the data. So I think it is 10 now. Maybe we can take break for 5 or 10 minutes and before we go to next lecture.